Now the question number 25. Given that oxidation of succinate ion produces ethylene and carbon dioxide gases. Okay, so let's just draw the succinate ion. This is our succinate ion. Okay, so this on oxidation produces ethylene gas and carbon dioxide gases. Now let us see the reaction. If it loses 2 electrons, 1 electron from this, now this oxygen has a negative charge, it means it has 1 extra electron. So normally oxygen has 6 electrons. Now this is supposed to have 7 electrons. 2, this is third, 4, 5, 6, 7. Similarly here 2, 3, 4, 5, 6, and this is the 7th one. Now this oxygen and this oxygen both will lose 1 extra electron to finally form this neutral species where the oxygen will have 1 odd electron. So 2, 3, 4, 5, 6. Okay, now this one we can say this bond has 2 electrons, this bond has 2 electrons. So this carbon, it will take 1 electron from this side, 1 electron this one, they will combine, 1 electron from this side, and 1 this odd electron combines, and these odd electrons are retained by these carbons. So after this we will get this part will go out as CO2, this one and this one. These two will move out as 2 CO2 molecules, and what remains is CH2 radical, single bond CH2 radical, which will finally join to form CH2 double bond CH2. Okay, so this is how the ethylene and carbon dioxides are produced. Now the point is, in this reaction 2 electrons are used. If this is 1 mole, then we are using 2 mole electrons. 2 mole electrons means 2 Faraday charge. So we can say 2 Faraday charge produces, now this is 1 mole, so 2 mole CO2 were produced. So means 2 Faraday produces 2 mole CO2 plus 1 mole C2H4. Now 0.2 Faraday will produce 0.2 mole CO2 and 0.1 mole C2H4. Now this is oxidation part. So this is taking place at anode. Okay, so these are generated at anode. So we can say 0.3 mole gases are generated at anode. Now he is given potassium succinate, means we have a K positive here, another K positive here. So in the electrochemistry chapter, you know that reduction takes place at cathode. So at cathode, if you think that K positive will finally gain electron to form potassium solid, this does not take place. Why this doesn't take place? Because here the competing reagents, okay, or the competing ions, K positive will try to gain the electron, but another competing one is water also. Water will also compete against it. So the 2H positive from the water can also gain electron and form H2 gas. This reaction has a higher reduction potential because its reduction potential is 0, standard hydrogen electrode. But for this reaction, for alkali, the reduction potentials are negative. So since this has a higher reduction potential, this is going to take place. So at cathode, 2 mole electrons will generate 1 mole H2, means 2 Faraday will generate 1 mole H2. So 0.2 Faraday will generate 0.1 mole H2. So 0.1 mole H2 is produced at cathode, 0.3 mole gases are produced at anode. So total moles of gases produced at cathode plus anode is equal to 0.4 mole. And since we have been given STP conditions, 1 mole of an ideal gas at STP occupies 22.4 liters. So volume occupied is 0.4 into 22.4 liters, that is 8.96 liters. So the answer should be fourth option. Next, 26th question, it's the Bal-Schimann reaction. So according to Bal-Schimann reaction, this is the reaction where fluorination is carried out. Because fluorination normally is so exothermic, we do not carry fluorination in normal conditions. Okay, it is always carried out indirectly. So the reaction is, if you start with aniline and you treat this in presence of tetrafluoroborates and NaNO2, it will convert to form diazonium salt. So we'll have N2 positive, BF4 negative. Now they have asked after this step that we are treating a diazonium salt. They are not given anything about this aniline. Okay, so reaction starts from here. Now after this, the step is just to heat this so that N2 and BF3 will move out and fluorobenzene is what remains. Okay, so what we need in the next step is only heat. So the answer should be 1, only heat. Next question, 27. The bond angles HXH. X is the central atom here. So in NS3 we know the bond angles is 107 degree, PH3 here 94 degrees, CH4 perfect tetrahedral 109.5 degrees, water everyone knows it is 104 degree. Because in water we have two lone pairs here, they repel. So because of that the angle reduces from the ideal 109.5 degrees. In NS3 we have one lone pair, so repulsions are not that much. So angle reduces from 109.5 but goes only up to 107. In PS3 also we have one lone pair, but nitrogen is more electronegative, so it will attract the electrons of this bond closer to it. So they have more repulsion in between. Phosphorus is not as electronegative, so electrons are a little away from phosphorus. Not towards hydrogen, but yes, in comparison to nitrogen, they are a bit away. So the repulsion between the bond pairs is less. So this repulsion becomes dominating and angle further reduces. So you can see the trend NS3, PS3, ASH3 and SBH3. The bond angle is reducing down the group. Same goes with group 16 hydrides also. Okay, so the answer here, greatest angle is CH4. Okay. And if you like the videos, then please like and subscribe.